Today we're going to prepare for exam number 5 on chapter 9, chemical quantities. And I'm working from the review document. And you can see that there are several highlighted ones. These are ones I want to be sure and get to. So let's go with number 1. Consider the calcium metal reacts with oxygen gas to form calcium oxide. Okay, so that establishes the chemical reaction that we're working with. Suppose we react 5.66 moles of calcium with 4 moles of oxygen. What is the number of moles of oxygen left over after the reaction is complete? So there are several clues that are given to us there. Well, first of all, we need the chemical reaction and balanced chemical. So calcium metal, of course, is a solid. And then oxygen gas is diatomic, right? Calcium oxide is the product. Okay, we know that's correct because oxygen is a chalcogen with a -2 charge. Calcium is an alkaline earth with a +2 charge. We only need one of each to balance. This is a type 1 compound. Now we need to balance. So we got 2 oxygens here, we need 2 there. Now we got 2 calciums. That's balanced. Now what are we given? We're given 5.66 moles of calcium and 4 moles of oxygen. All right, so how would you do that? Well, you'd probably do it in a sealed vessel, right? And you would introduce air into the vessel of a certain amount. We know what the percentage of oxygen is in air. Introduce that into the vessel so that you have 4 moles of oxygen with 5.66 moles of calcium. So remember when I said if you're given absolute amounts of 2 reactants, one of them is almost certainly going to run out first. The clue that they're giving us is the number of moles of oxygen left over. So they're telling us right now that oxygen is excess. And calcium is limiting. Okay? The problem tells us that. Now, we don't have to believe it, but we can prove it. If you have 5.66 moles of calcium, how many moles of oxygen will be required? All right. Dimensional analysis is what we need. Calcium, oxygen. Ratio is 2 here and 1 there. So we need just half of that value in terms of moles of oxygen. We need 2.83 moles of oxygen required. All right. So we got plenty. In fact, we have excess. So to answer the question, we need to know what's left over. Okay. 711 moles of oxygen remain. Okay. That was simple enough. Let's see what 3 has to offer. Okay, that one's given out. Sodium and water react according to this equation, and it's already balanced for us. All right, so we'll put the 2 sodiums plus water, and we need 2 of those. And that gives us sodium hydroxide in aqueous solution, correct? Yes. And hydrogen gas. All right. Now, what do we do with it? What number of moles of hydrogen will be produced when 4 moles of sodium is added to 1.2 moles of water? 4 moles, 1.2 moles. And the question is, how many moles of hydrogen? Okay. The go-to method for determining the limiting reactant is to calculate how much product is produced if all of one reactant is consumed, and then go to the other one and do the same thing and compare the results. But in this case, we've got a reaction ratio of 2 to 2 or 1 to 1. So we need 4 moles of water because they're 1 to 1 ratio. There's not enough. So that means this is the limiting reactant. And sodium is excess. So what we want to do then is take this one and find out how much hydrogen is produced, because this one will run out. Okay. Some more dimensional analysis. Water on the bottom, hydrogen on the top. The ratios are 2 to 1. Right? So 0.6 moles of hydrogen will be produced. Okay. And I'll skip a few and come down to number 5. In the reaction, nitrogen plus hydrogen yields ammonia. Good old Haber-Bosch process. How many moles of ammonia would be produced from 1.21 moles of hydrogen and excess nitrogen? Okay, in this case, we don't have to be concerned with determining the limiting reaction because we're already told what it is. Okay? We're told that we start off with 1.21 moles of hydrogen. And this is excess. Doesn't matter how much it is, because this one determines the extent of the reaction. So if the question is, how many moles of ammonia, we just need to convert hydrogen gas to ammonia. Okay? So the ratio is 3 here and 2 there. So 2/3 of 1.21. And I get, let's see, 3 significant figures. 0.807 moles of ammonia. All right. Number 6. Consider the following unbalanced equation. All right. There's a clue. We're probably going to have to balance it. let's see, C2H5OH. And then that's heated up to make it a gas plus oxygen. Should yield carbon dioxide and water. Okay. Oops. That doesn't make any sense. Yeah, maybe it does. We're going to take them at their word. Okay, now let's balance this equation. And for this type of equation, it's probably best if we use the budget method. So we've got carbon, hydrogen, and oxygen. On this side, we have 2 carbons. We have 5, 6 hydrogens, and 1, 2, 3 oxygens. On this side, we have 1 carbon, 2 hydrogens, and 3 oxygens. Okay? So we're going to hold the oxygens till last, and it's really a no-brainer because they're already balanced. Now, we're probably going to throw them out of balance and then have to come back. But I'm going to start with carbon. We need 2 carbons. That gives us 2 carbons. It gives us 4, 5 oxygen. Okay? Now we'll go to hydrogen. We've got 6 hydrogen on this side. We need 6 hydrogens on this side. So that would be 3 plus 4 is 7. Okay? So now we need 7 oxygens on this side. But notice oxygen occurs in 2 places, here and there. So if we leave this one alone, then we only need 6 more oxygens. So if I put a 3 here, that would be 6 plus 1 is 7. And now our equation's balanced. And we can work with that from this point on. All right, more information. 1.7 grams of ethanol. That's this thing right here. Okay? And 11.2 grams of oxygen. I'm going to put it down here. 11.2 grams of oxygen. Because I want to string the conversion across like that. How many moles of carbon dioxide are produced? Right? So we have to determine which one of these is limiting. If we convert this to carbon dioxide, then we need to go first. We've got to convert it to moles. Remember, you can't go anywhere in an equation stoichiometrically without knowing moles. So we need the molar mass of this one. 2 carbons, 6 hydrogens, and 1 oxygen. All right, 24.02, 6.06, and 16. That's 46.08 grams per mole. So 46.08. That, and that will give us 1.7, 3.689 times 10 to the minus 2 moles of ethanol. That's my abbreviation for ethanol. Now we want to convert this to carbon dioxide. So ethanol on the bottom, carbon dioxide on the top, and the ratio is 2 here and 1 there. All right. So I just say 2 times, and that gives me 7.38 times 10 to the minus 2 moles of CO2. And then we'll use this one for oxygen, grams per mole, 16 for 1 oxygen, 32 for the molecule. Right? So 11.2 and 32 divided. This is 0.3500 moles of oxygen. And then we want to times that oxygen and CO2. So we have 3 oxygens, 2 CO2s, and that gives us 2.33 times 10 to the minus 1 CO2. So which one produces the least amount? This one right here. So that's our answer. Well, standard notation, all right? So 7.38, move the decimal 2 places to the left. 1, 2. Right. So it's 0.0738. That's their answer. All right, number 7. Okay. Fe2O3, iron 3 oxide, they give us the molar mass, reacts with carbon monoxide according to this equation. When 185.5 grams of carbon monoxide reacts with excess iron 3 oxide, how many moles of iron will be produced? All right, so our balanced equation is Fe2O3 plus carbon monoxide, right? 3CO yields iron. Now they put CO2 first. Let's do that. 3 CO2s plus iron. Okay. And now, what are we told? 185 grams of carbon monoxide. Okay. React with excess. Okay. Excess. That means we can focus on this one. All right. So this has to be converted to moles. Carbon monoxide they gave us as 28 grams per mole. All right. 185.5 and 28. So this is 6.625 moles carbon monoxide. And then moles of iron. So this is moles of iron produced. Okay. Now what we have to do is convert CO to iron. So iron is 1 and CO is 3. So we just divide this by 3. That's 2.2. Let's see, we had 4 significant figures. 08 moles of iron. Okay. That was fairly simple. And we're down to number 10. Oh, let's see, the following equation. This is a combustion reaction. Right? Ammonia reacts with oxygen to produce nitrogen dioxide and water. All right, so 4 ammonia gas reacts with oxygen gas in the ratio of 7 to 4. And we produce 4 NO2 and 6 water. Okay. Now, what are we given? How many moles of ammonia will be required? Moles of ammonia required to produce 11.9 moles of water. All right. So what does that mean? That means that we have to assume oxygen is excess. We're not going to run out of it. We're going to use all of, well, we're going to use all of this to produce that, but now we're working backwards. And there's no mystery to that. Dimensional analysis will get you there. Water and ammonia. That's the ratio. 6 water, 4 ammonia. So we just take 11.9, divide by 6, and multiply by 4 with 3 significant figures. Okay? And this is theoretical. This is ideal. This is 100% conversion. We're not interested at this point in efficiencies. All right, we'll skip a few and come down to this one. Number 13. All right. Let's try another one. Okay. Unbalanced equation. All right, so this is Na2SiF6. Na2SiF6. Sodium. Let's see, this is solid plus sodium solid yields silicon and sodium fluoride. Okay. Now, we're told this is unbalanced, so we've got to do our job. Let's see. We could use the budget method, right? But this has two elements that are going to help us rectify any differences. So I'm going to say 2 sodiums, we need 2 on this side. Right? 2 sodiums. Now we need, you know what? We need 6 fluorines. Let's do it this way. 6 fluorines. Okay, got the fluorines. Now we've got, you know what? We need the budget method. I should have seen this one coming. Because we've got sodium in 2 different places. We've got, it's going to mess things up. So let's do the budget method and just make it easy on ourselves. And, oops, that's not right. It's 3. And 1 and 6. So 7, 10. 1, 2, 3, 9, 10. And sodium here is 1. Silicon is 1. And fluorine is 1. Okay. Now we can keep the sodium and silicon free. We're going to work with fluorine again. So this is going to be 6. And now we have 6 sodium on this side. Okay. Let's see. What would be the best way to accomplish this one? If we leave that one, if we leave this one alone, then we don't have to mess with silicon. So instead, if we say we've got 2 sodiums here, so if we put 4 here, that's 6, right? And that balances the equation. That type of reasoning comes with practice, right? You don't practice balancing equations, then sometimes you get stumped. If 3.09 moles of silicon were produced, okay, how many moles of sodium fluoride were also created? All right. So this, let's do it over here. 3.09 moles of silicon. We're just going to find out how much sodium fluoride was also produced. And the ratio is 6 to 1. So 6 times that should be about 18.5 or so. Yeah, 18.5. Let's cancel. Dimensional analysis comes to the rescue. All right, we'll skip a few. Come down to number 18. It's getting weak. Try this one. How many atoms of aluminum can be produced by the decomposition of 31.5 grams of aluminum oxide? Yep. Decomposition will do what? If we're going to elemental decomposition, we'll have aluminum, okay, and oxygen, like that. Okay, so balance the equation. We need 3 and 2 oxygens. So let's say, take that 2 and put it over here. Take this 3 and put it over. So now we have 6 oxygens. We also have 4 aluminum. And that's a balanced equation. Okay. Decomposition of 31.5 grams. Of aluminum oxide. How many atoms of aluminum can be produced? All right, so we need to convert this to moles first. Right? So we need 2 aluminum, which is 2698. We're not told, are we? No, we're not given the molar mass. And then 3 oxygens. That's 101.96. Divide that into 31.5. And I get 0.3089 moles of aluminum oxide. Okay, now we want to convert that to aluminum. Right? So what we need is aluminum oxide here and aluminum there. So 4 for aluminum, 2 for aluminum oxide. So we multiply that number by 2, which is 0.6179 moles of aluminum. Okay, we're not done yet because it asks for atoms. We need another conversion. What's the conversion from moles to atoms? Avogadro's number. So we'll multiply that one times 6.022 times 10 to the 23rd. And 3 significant figures is what we're allowed. So let's see, 3.72 times 10 to the 23rd atoms. Okay. Let's see, we'll skip a few repetitive ones. Come down to 23. All right. Calculate the mass of water produced when 9.47 grams of methane react with an excess of oxygen. All right, we're going to combust oxygen. Combust methane with oxygen. And the equation is unbalanced. This one, though, is very well behaved when it comes to balancing. Carbon dioxide and water, yes, indeed. Okay. So, we're going to hold oxygen to last. We've already got 1 carbon. We need 4 hydrogens. Here we go. 4 hydrogens. Now we have 2 plus 2 is 4 oxygens. Right? That should be balanced. 1 carbon, 4 hydrogens. 2 times 2 is 4. 4 oxygens, 2 plus 2, we're balanced. Now to the question. 9.47 grams of methane. Okay? And we want to know, well, this is excess. Right? So that's not going to run out. And the answer, what we want is the mass of water. So we want grams of water. First of all, we have to convert this to moles. Right? So that's 12.01 and 4.04 for the hydrogens. 1605. Divide that into 9.47 and get 0.5900. And this is moles of methane. Now we want to convert that to water. Water's on top, methane's on the bottom. So the methanes cancel. We need a ratio. 2 waters, 1 methane. Right? So that gives us 1.180. Excuse me. Moles of water. Now we can convert water back to grams. Okay. So the magic number for water is 18.02. And we can keep 3 significant figures. 21.3 grams of water should be produced. Okay. All righty then. 26. Let's see, we have aluminum carbide plus water. All right. Aluminum carbide plus water yields what? Aluminum hydroxide and methane. Okay. Let's see. How many moles of water? Okay, we have to balance the equation first. So let's go ahead and do that. 4 aluminums, 3 carbons, 2 hydrogens, 1 oxygen. 1 aluminum. Let's see, 1 carbon. Hydrogens. 3 plus 4 is 7. 7 hydrogens. And oxygens, 3. Okay. So let's see. There are no free elements, so we can start wherever we want. Let me see if there's anything magical about this. I'm going to start with aluminum. So if we put 4 here, that gives us 4 aluminum, changes the number of oxygens. So 3 times 4 is 12 oxygens. Okay. Hydrogens, also 12 hydrogens plus 4 is 16. Right? Carbons. Okay. Carbon, 3. Okay, 3 carbons on this side. That's good. Changes the number of hydrogens. So we still have 3 times 4 is 12, and then 12 hydrogens here is 24. Okay. Now if we need 24 hydrogens and 12 oxygens, if we put a 12 here, that's 24 and 12. 24 and 12. And we're balanced. We didn't do that step first. Oops. Why did I do that? And let's see, that was, that's it. There's no coefficient for this one. Right. Okay. Now we can go ahead with the solution to the problem. What we're given, 206 grams of aluminum carbide. Okay. How many moles of water are needed? So we're looking for moles of water. If we use up all of this, how many moles of that are required? So what we need first is molar mass. So we need 4 times 26.98 for aluminum and 3 times carbon. I get 143.95 grams per mole. 143.95 divided into 206 gives me 1.431 moles of aluminum carbide. All right. Now we need to convert to moles of water. So aluminum carbide and water. The ratio is 1 to 12. So we're going to multiply 12 times that and say we can keep 3 significant figures. 17.2 moles of water. 17.2 moles of water will be the required amount of water. Okay. All right, 29. Consider the following reaction where X represents an unknown element. 6 of the X plus 2 of the diboron trioxide yields B4X3 plus 3XO2. If 165 grams, let's see. Oh, okay. That other problem I've got in blue, that's a separate problem altogether. We're going to solve the first one. So let's write the balanced equation first. 6x, we're saying it's a solid, and B2O3 plus 2 B2O3 solid produces B4X3 plus 3XO2. Okay. Yeah, that's balanced. That's okay. We're good. That equation's balanced. 165 grams of X reacted with diboron trioxide to produce 2.29 moles of this compound. 2.29 moles of that compound. What is X? All right. There are two ways to determine the identity of an element. One is the atomic number. If you don't have the atomic number, the number of protons, then your second possibility is molar mass. So we're going to have to go with molar mass here. We already have the mass. We just need how many moles does that represent? Right? 165 grams per how many moles? Right? All right. We know that we have this many moles of product, and we know the ratio of these two. So we can take that and find out how many moles of this we have. All right. The ratio B4X3 and X is 6 here and 1 there. So I'm going to say 2.29 times 6 is 13.74 moles of X. Now we know what this is. 13.74 moles divided into 165. And I get 12 point, let's see, 3 significant figures. 12.0. Actually, if we go to 4, it rounds off to that. Grams per mole. All right, so you go to the periodic table and you say, all right, we follow left to right, top to bottom, and keep going incrementally until we find one that has a molar mass that's close to this value. And as it turns out, that is carbon. All right. Now I want to take this other one that I proposed. Let's say we have X and 3F2. X plus 3F2 yields what? Yields XF6. XF6. And we're also told that X is 235.2 grams. 235.2 grams. And then XF6 is 347.9 grams. 347.9 grams. Okay, what's X? Again, we're going to have to go with molar mass. 235.2 grams, and then how many moles on the bottom? How do we get that? We got grams of this one, but we don't know the molar mass because we don't know what X is. So we do have fluorine over here. If we can find out how many grams of fluorine we have, then we can calculate moles of fluorine and work back to X. So remember Lavoisier's rule, conservation of mass in a chemical reaction. This mass plus that mass equals this mass. So this would be, say, Y grams. So these two yield that. That means F2, the mass of F2 is equal to 347.9 minus 235.2. So that's 7, 2, 1, 1. 112. That's how many grams of F2 we have. Now we can convert that to moles. Right? So F2 is going to be 2 times 19, which is 38. 38 into, let me be sure I got that one right. 2. Yes. Okay. Then divide that by 38. And this is 2.966 moles of F2. Now we can convert that to our X. And the ratio is 3 to 1. Okay? So I divide that by 3 and I get 0.9886 moles of X. Now we can put that in here. 0.9866 of 886, excuse me. Yeah. 886. There we go. Divide that into 235.2. Oops. 235.2 divided by 0.9886. There we go. Equals 237 point, not 8, rounded off to 9 grams per mole. So we go to our periodic table and say, all right, what's close to that? And we work our way down. And the closest one that we can come to rounded off is approximately 238, and that is uranium. So X is equal to uranium. $32. All right. Which of the following reaction mixtures would produce the greatest amount of product? assuming all went to completion, each involves reactions symbolized by this equation. So we got Haber-Bosch again, N2 plus 3H2 yields 2NH3. Okay. So we've got A through C. Excuse me, A through E. Okay, the first one, 1 mole of nitrogen, 3 moles of hydrogen. 1 mole here and 3 moles there. So what would that produce? That's a stoichiometric mixture. 1 and 3 produces 2. Right? But the next one, 5 and 3. Okay? If we use all of this, we're going to need 15 of these. So this is our limiting. So 3 of these produces 2 of those. Okay? This one says all the same. So we got to go to D and E to see if that's true. So 1 mole here and 6 moles there. Right? 1 mole of this needs 3 of that. So this one's going to run out. 1 produces 2. Okay? And the last one, 3 and 3. 3 moles here and 3 moles here. This 3 would require 9 hydrogens. So hydrogen's going to run out. 3 produces 2. So our answer is all the same. 33. Mint. Right. Okay. And we mark comma present. Zoomed in. Okay. See, we're up to 33. Balanced equation, P4 plus what? Hydrogen. 6H2 yields 4pH3. 4pH3 gas. Let's see. 4 and 4. 3, 4, 12. Okay. That's balanced. 5 moles of hydrogen, what? We have 5 moles of hydrogen. Let's see. What are our choices? First choice says cannot react with phosphorus. That's patently false. Reacts with 2.5 moles. 2.5 moles of P4. No, if it's 2.5 moles of P4, then we need, let's see, 3 times, we need 15 here. Right? That won't work. There's not enough P4. So that was false. Produces 3.3 moles of pH3. Produces 3.3 moles pH3. So 2.5 moles. If we take 2.5 and apply our conversion factor in pH3, Then we have 1 here and 4 there. So 4 times this is 10. That says 10. That won't work either. How about tells us that 5? Oh, wait a minute. Shoot. I'm working from the wrong assumptions. All right, let's start over again. I have to edit that one. This is our starting point. So, will 5 moles react with 2.5? Cannot react. All right, well, that one's true, still true. 2.5 moles P4. Right? How many moles does it need? If this is 6, or this is 2.5, then it needs 15. Right? That's false. If we're still going with 5, for C, produces 3.3 moles of pH3. So 5 moles here, does it produce 3.3 moles of that? Well, if we start off with 6, H2, and we want to convert it, right? So we have 6 here and 4 there. Does that equal? Yes, it does. That one's true. And we found our true one, and there are no wonky ones in there. Well, there's one, but we threw that one out already. So D and E should also be false. We found a true statement right here. All right, skip some redundant ones and go to 39. Consider the reaction of magnesium metal with hydrochloric acid to produce magnesium chloride and hydrogen gas. All right, if we're going to work this one, we've got to write the balanced equation. Magnesium metal reacting with what? Hydrochloric acid. To produce magnesium chloride. Let's see, that's soluble. Aqueous solution. Plus hydrogen gas. Okay, now we need to balance it. This one should be fairly well behaved. We need, let's see, 2 chlorines on this side. That gives us 2 hydrogen. That's balanced. Now we can go to the conditions. 4.52 moles of magnesium. And 4.52 moles of hydrochloric acid. Okay? And the question is, how many moles of hydrogen are produced? We can assess this one for the limiting reactant very easily. This needs 2 times that much of hydrochloric acid, right? But it only has the same amount. So magnesium is limiting. Excuse me, magnesium is not limiting. We've only got enough hydrochloric acid for half that amount. So if we do this, 5.2 moles of HCl, and we convert it to magnesium, then that's going to give us, let's see, 2.26 moles of magnesium. That's all we need for magnesium. So this one is excess. This one's limiting. So we're going to go ahead from here and convert that to hydrogen. Well, the ratio here is the same between hydrochloric acid and hydrogen as it is between hydrochloric acid and magnesium. So we should get the same number of moles. This is 1, this is 2, and this is 2.26 moles of hydrogen. All right. That was fairly easy. Let's see. We'll stop at number 43. Three. So we're using this following equation. Let's see. 4 ammonias plus oxygen, and 7 of those, and then 4 NO2 and 6 water. There we go. How many molecules of water are produced from 9.12 moles of NO2? If that much is given off. Let's say 9.12. 9.12 moles. So if we have this many moles of NO2 produced, how much water will go with it? This is a very simple unit conversion. Let's see, this is NO2. And we want to cancel the NO2s and leave us with water. So the ratio is 6 here, 4 there. 6 and 4. So let's see. 9.12 times 6 divided by 4. So this is 13.7, 3 significant figures, moles of water. Oh, was that the question? How many molecules? Okay, we're not done yet. 13.7 moles of water. Now we have to convert that to molecules. That's 6.022 times 10 to the 23rd. Three significant figures, 8.24 times 10 to the 24th. Molecules. Okay. Scroll. 45. Tin-2 fluoride is added to some dental products to help prevent cavities. Manufacturers have to make tin-2 fluoride first before they can add it to their products. So tin plus hydrofluoric acid yields tin-2 fluoride plus hydrogen gas. How many grams of tin-2 fluoride can be made from 49.6 grams of hydrofluoric acid if there's plenty of tin available? All right, so our equation is this one plus hydrofluoric acid. And yes, that's named correctly because it's in aqueous solution. And now we've got tin-2 fluoride in aqueous solution plus hydrogen gas. Now, let's see, 2 here. Is that balanced? 110, 110. 2 fluorines, 2 fluorines, 2 hydrogens, 2 hydrogens. That's balanced. How many grams of tin-2 fluoride, right, can be produced from 49.6 grams of hydrofluoric acid? All right. First thing you got to do is turn it into moles. We can't go anywhere in this problem unless we know moles. So we need HF, which would be 1.01 for the hydrogen and 19.00. So it'd be 20.01. There. That'll give us moles of hydrofluoric acid. And that's 2.4788 moles of HF. Now we can convert that to moles of 10-2-fluoride. Ratio is 2 of these, 1 of those. So we just take half of that, 1.2394 moles of 10-2-fluoride. Now we're going to convert it back to grams. So we need to know the molar mass of 10-2-fluoride, right? SNF2. So 10 is 118.71. And then 2 times 19 for the fluorine. That. Go 150. 6.71 grams per mole. 156.71. So we need to convert this to grams. 156.71 times that value. Let's see here. So it's 194. 3 significant figures. 194 grams. 194 grams of 10-2-fluoride can be produced. And we're skipping quite a few here. Lots of repetition. Multiple problems to give you practice. Down to 60. Okay. All right. This theoretical equation, 2 A's plus a B yields what? 3 C's and a D. Okay. 3.35 moles of A. And 2 moles of B. React to form 4 moles of C. 4 moles of C. Okay. What's the percent yield of this reaction? All right. The calculation that we did before in the lecture part of the course was in terms of grams per grams. Theoretical in the denominator, actual in the numerator. We're going to work with moles instead, right? Because that's all we have to work with. So we don't have any choice. What we need, this is actual. We need theoretical. So first thing we have to do is decide which one of these is limiting, right? Well, if we say 3.35 moles of A converted to A to C, then the ratio would be 2 and 3. So 1.5 times 3.35 is 5.025. 0.025 moles of C. And then if we use 2 moles of B and convert that, we still got 3 here, but now we only have 1 there. So that's 6. Right? This is our limiting. So this is how much theoretical that we would produce. Now we can do our calculation. Over 5.025 times 100. And 3 significant figures is 79.6% efficiency. Okay. Actually, we should get the exact same value, because if we convert this to moles of C, and this, to grams of C, the same factors are being used top and bottom. So they would cancel out, we get the same ratio. So this is an effective way of assessing percent efficiency, percent yield. 61. All right. Calculate the molecules of oxygen required to react with 25 grams of sulfur in the following reaction. All right, so we're starting with this balanced equation. We got sulfur and oxygen yields sulfur trioxide. So we got a synthesis reaction here. 25 grams of sulfur. Okay. And the question is the number of molecules of oxygen required. So this has to be converted to moles first. Always convert to moles. So sulfur is 3207. And 32.07 is 0.7795. That's moles of sulfur. Now we need to know how much oxygen is required. The ratio is 2 here, 3 there. So 2. The question was how many molecules? So now we have to convert this to molecules. And the magic number, Avogadro. Oops. 10 to the 23rd. There we go. And I get 3 significant figures times 10 to the 23rd molecules. Okay. Let's see, what else we got? Highlighted, let's see, 69. In the reaction between carbon monoxide and Fe3O4, The theoretical yield in an experiment is calculated to be 47.2 grams. When a careless chemistry student carries out the experiment, the actual yield is 37. Calculate percent yield. There's a lot of fluff in here. We're given the information we need to calculate percent yield in the problem. All we have to do is plug it into the formula. The actual amount is 37 grams. The theoretical amount is 47.2 grams. So it's a one-step calculation. And I get 78.4% yield. Okay. Number 70. .1 mole sample of potassium chlorate is decomposed according to this reaction. Okay. Potassium chlorate is a solid, I do believe. Yes. And decomposes into potassium chloride, solid, plus oxygen. And that's 3. Okay. How many moles of oxygen are formed assuming 100% yield if 3.1 mole sample is decomposed? It's like we're going backwards. This is simpler than the previous, any of the previous ones. So the question then is, how many moles of oxygen are formed? Right. This is a simple dimensional analysis conversion. So we have KClO3 goes to oxygen with 3 and 2. So 1.5 times this would be 6.2, about 7.6 or thereabouts. Oh no, my mistake. I better use my calculator. Yeah, 4.7. All right. $71. Let's see how we're doing on time. 30. Okay. Should be able to finish. 3.4 moles of iron react with chlorine according to this reaction. So we got a synthesis going on here. And 3 chlorines yields 2 . Is that right? Yeah, that's right. Yeah. Okay. Question. 3.4 moles of iron. And how many moles of chlorine are required? All right. This is a one-step problem. So we have iron here, chlorine there, 3 and 2. So 1.5 times 3.4. 5.1 moles of chlorine. Okay. Some problems are simple, some are not. 72. Ammonia reacts with oxygen to form nitrogen dioxide in water, according to this reaction. All right, so we have 4 ammonias and reacts with oxygen. The yield. Oops. Or NO2 plus 6H2O. There we go. And you react ammonia with oxygen. At the end of the experiment, you find that you produced 23 grams of water. So we get 23 grams of water out of this, plus, and have 8.52 grams of ammonia left over. So 8.52 grams remain. Right? So what that means is we ran out of oxygen, right? Because we had some leftover ammonia. What's the mass of oxygen reacted? All right. This is typical of word problems. They try to confuse you. If you don't understand what's actually happening and what the question is, the mass of oxygen reacting, we want to know that. So if all of this oxygen is used up to produce this much water, we don't need to know this. That's extra information that's not essential to solve the problem. We just need to convert this to moles and work back to that. So we're going to convert grams of water to moles of water first. And I get 1.2764 moles of water. Then we're going to convert that to moles of oxygen. Which is 7 here and 6 there. Let's see. 7 times 6 divided. And that gives us 1.489 moles of oxygen. Now we can convert that back to grams, which would be 32, right? 16 for each oxygen. We got 2 of them in that molecule. 32 times. And this is 3 significant figures, yes. 47.7 grams of oxygen. Okay. Number 73. For this reaction, C2H4, that's ethene, and oxygen, combustion reaction, carbon dioxide and water as products, 5.5 moles of CO2 are produced. How many moles of O2 were reacted? All right, so this is our balanced equation. It's oxygen yields CO2 plus water, and the coefficients are 322. 3, 2, 2. Okay, we're given 5.5 moles of CO2 are produced. And the question, how many moles of oxygen were reacted? Okay, 5.5 moles of CO2 converted to oxygen, 3, and 2. Oops. Say 2 and write 3. That won't work. 5.5 and 3. Excuse me. 5.5 and 3 times 2 divided. 8.25 moles of oxygen were required. Let's see. Why does it only say 8.2? Because we had 2 significant figures. Actually, I would say 8.3. There's a rounding error in there somewhere. So pick the best answer. If you pick D because you came out with 8.3, then technically you would be right, but I might mark it wrong because I'm expecting C. If that's the case, then you got to contact me and point that out so that I can give you credit for it. And that applies to any problem. As long as you're rounding it correctly and your answers come out different, and the multiple choice gives you an option to say none of the above. 75. If you don't have a choice like that, then you pick the best answer. All right, we balanced this one once before. If 1.86 grams of ethanol react with 14.3 grams of oxygen, how many moles of water are produced? So we got to balance this equation again. C2H5OH, and this is gas, plus O2, CO2, and water. All right. Well, we got to do it again. Let's balance this equation. All right. 2 carbons, 6 hydrogens, and 3 oxygens. 1 carbon, 2 hydrogens, and 3 oxygens. So we'll go to carbons. Makes 2 here, and that's 4, 5 here. And then hydrogens. Let's see. We got 6 on this side. We need 3 there. 6 on that side. And then we need, let's see, did I do that? No, I haven't finished. Sorry. 3 plus 4 is 7. That's 7. Okay, now 7 on this side. We've already got 1 here. If we leave it alone and just adjust this one, then 6 of those plus 1 of these is 7. Okay, so now we're balanced again. Now we can answer the question, which is 1.86 grams of ethanol and 14.3 grams of oxygen. Okay. How many moles of water are produced? Okay, we got to find the limiting reactant. So we're interested in how many moles of water are produced. So we got to convert each one of these to moles. And then see which one produces the least amount of water. Right. Let's see. 2 times 12.01 and 6 times 1.01 and 1 times 16. 4.02. 6. This is 46.08 grams per mole. So 46.08. I'm going to go ahead and convert this one since it's already in my calculator. And I get 4.0365 times 10 to the minus 2 moles of ethanol. Okay. And this is oxygen, which is 32. Divide that into 14.3 is 0.4469 moles of oxygen. Then we're going to convert, make some room here. We're going to convert all of this to water. All right, that's 3, that's 1. So 3 times that value. Let's see, I'm going to flip this one. 3 times is 0.1211 moles of water. And then we're going to take that one and divide by, multiply. Let's see. We need a conversion factor first. O2 and H2O. So this is 3, and this is 3. So that's equal to 4,469 moles of water. Okay? So which one produces the least amount? This one, that one. This is the least amount produced. How many moles of water are produced? 0.1211. Best answer is E. And there's 80. Yep, we still got time. All right. Nitrogen gas reacted with hydrogen gas to produce ammonia. All right. We need 2 nitrogens. That gives us 6 hydrogens, and that's balanced. Now we're given 22.5 grams of nitrogen and 22.5 grams of hydrogen. Determine the mass of ammonia that can be produced from these 2 reactants. All right. Hydrogen molecule only weighs about 2 grams per mole, whereas nitrogen weighs about 28 grams per mole. So this is going to be less than a mole, and this is going to be about 10 moles, right? So if this is less than a mole times 3, it's only going to be at most 3 moles, and this is going to be 10. That's not enough, right? So this one is limiting. This is excess. Now, if you can't follow that reasoning, then go ahead, convert that to moles, and say, what's the least amount that it can produce in terms of ammonia? Then solve it that way. It'll take you longer, but if that's the way you want to go, that's perfectly fine. I've determined that this one is limiting by reasoning the ratio of nitrogen and hydrogen in terms of moles. All right, so I'm just going to convert this one to moles. All right, so 14.01 times 2, 28.02. Divided into 22.5. And that's 0.8030 moles of nitrogen. Then we're going to convert that into moles of ammonia. And that's 2, that's 1. So just 2 times that. yields 1.606 moles of ammonia, and then we'll convert it back to grams. For ammonia. So that would be, ammonia would be 14.01 plus 3.03 for the hydrogens. So that's 17.04 times 1.606. Rounded off to three significant figures, which is 27.4 grams of ammonia. Okay. 83. Okay. Coming down to the wire here. Number 83. Fe2O3, they give us the molar mass, reacts with carbon monoxide. According to this equation, 470 grams of iron 3 oxide reacts with excess carbon monoxide. Number of moles of iron produced. All right, that should be fairly simple. Fe2O3 and carbon monoxide yields 3CO2 plus 2 iron. That looks to be 3 and 3 is 6. Yeah, that's balanced. Okay. 470 grams of Fe2O3. Right? Excess carbon monoxide. Okay. So we're going to convert all of that. Number of moles of iron produced. So we got to make moles of Fe2O3. And the molar mass is given as 159.7. If I calculated it, I'd have another decimal, but we're going to use that information so that we don't have the chance of a rounding error in the answers. So let's take 470 and divide by 159.7, which is 2.943. That's moles of Fe2O3. Then we want to convert to moles of iron. Fe2O3 on the bottom, Fe on the top. This is 2, that's 1. So I just say 2 times that, and I get, let's see, was that the question? Moles of iron. Okay, so I'm going to go ahead and round 4 places. 5.886 moles of iron. Okay. And 84 coming up. Okay, which of the following statements is always true concerning the reaction represented by the following balanced equation? All right, so we have 2C2H6, which is ethane, and 7 oxygens yields 4 CO2 plus 6 water. And they're all gas. All right. All right. A says none are true. None true. That means we have to look at the others. All right, if we find one that's true, then A can't be true. If we have an equal number of moles of C2H6O2, there's no limiting reactant. All right, if we have equal number of moles, let's just say we have 2 moles. 2 moles of this, let's say 2 moles here. That's an equal number. How many moles of oxygen would be required? Well, it'd be 7 to 2, right? It would be 7 required. 7 moles required. Right? So oxygen is limiting. B says no limiting reactants. Can't be. That's a false statement. If we have equal masses of C2H6 and O2, equal masses. All right. So if we have equal masses, let's say, let's pick, we need the molar mass of C2H6. And 6 hydrogens. .02 and 6.06. That's 30.08 grams per mole. All right. So let's say we have exactly 2 moles of C2H6, and that would give us 60.16 grams. So let's say we have 60.16 grams here. That's equal to 2 moles of, because all it says is equal masses, right? Equal masses. So we can pick what mass. If we have 60.16 grams here, how many moles does that represent? Well, we divide by 32, don't we? So that means we have 1.88 moles. Is that enough? Right? That's 2 to less than 2. So that one, wait a minute. Let's see, equal masses. There's no limiting reactant. Yes, there is. Oxygen is limiting. Right? So C is false. How about D? If we have more mass of O2 than C2H6, then C2H6 must be limiting. Okay, if we have more mass here, well, let's say we have, let's just say we have 61 grams. More mass. It's still not enough, right? So C2H6 must be limiting. Actually, O2 is still limiting. So how about the last one? If we have more mass of C2H6, then O2 must be limiting. Yes. Right? Because if we have equal masses, O2 is limiting. Any more mass of C2H6 would still make it limiting. That one is true. So E is a true statement. All right. Any more? Let's see. No, I think that's it. Yep. That was the last highlighted one. Now, if there are any that I missed that you want to deal with, then we got time to do that. We got 10 more minutes. We can do another problem if you'd like. Otherwise, we're done for the day, and we won't be back until the week after next. Next week is spring break. So it'll be, let's see, that was Tuesday was the 10th, it'd be the 17th. No, 10th, 17th, and be 20. Oh, 24th. Yep. We'll be back on the 24th, and on that day, the exam on this material will be due by midnight. And then If nobody shows up in class to take the exam, then I'll go ahead and jump into the next material, which is chapter 15 on solutions. We'll get that one when we come back from break.